With higher quality images and greater compression ratios, JPEG XL is being developed to outperform other web image formats such as PNG, JPEG 2000, GIF, and WebP. Existing JPEG files can be losslessly encoded as JPEG XL files and restored to the original JPEG files, which is an improvement over prior JPEG codecs and file formats. To reconstruct the original JPEG file, the JPEG XL bitstream reconstruction data employs the image data as well as any other information present such as XIF, XMP, or JUMBF. This intrinsic compatibility enables a smooth transition from JPEG to JPEG XL without the need to store two files. Content: JPEG XL introduction, JPEG standard, why DCT and not DFT demo included, JPEG XL codec architecture. In this we have XYB transform, integral transform, adaptive predictor, adaptive quantization, DC handling, AC encoding, loop filters, entropy coding, then JPEG recompression mode. Source picture examples are clustered into 8x8 blocks at the encoder's input, shifted from unsigned integers with range 0, 2 power p minus 1 to unsigned integers with range minus 2 power p minus 1, 2 power p minus 1 minus 1, and fed into the forward DCT or FDCT. The inverse DCT or IDCT delivers 8x8 sample blocks at the decoder's output to form the reconstructed image. The idealized mathematical formulas of the 8x8 FDCT and 8x8 IDCT are as follows. Encoder FDCT. Each 8x8 block of source picture samples is a 64-point discrete signal that is a function of the x and y spatial dimensions. Because sample values typically vary slowly from point to point across an image, the FDCT takes such a signal as its input and decomposes it into 64 orthogonal basis signals called DCT coefficients, whose values are uniquely determined by the 64-point input signal. For a typical 8x8 sample blocks from a typical source image, most of the spatial frequencies have 0 or near 0 amplitude and do not need to be encoded. Decoder IDCT. The IDCT reverses the processing step at the decoder. By summing the basic signals, it reconstructs a 64-point output picture signal from the 64 DCT coefficients which have been quantized at that point. In terms of mathematics, the DCT is a one-to-one mapping between the image and frequency domains for 64-point vectors. The DCT in theory causes no loss to the raw picture samples. It just transforms them to a domain where they can be encoded more effectively. Different encoder, different outputs. The existence of a transcendental functions in the FDCT and IDCT equations is a fundamental characteristic. As a result, no physical implementation can calculate them perfectly. What's best in software for a general purpose CPU is unlikely to be best in firmware for a programmable DSP, and is almost certainly poor for specialized VLSI. Quantization. After receiving output from the FDCT, each of the 64 DCT coefficients is equally quantized using a 64-element quantization table, which must be supplied as an input to the encoder by the application or user. Each element can be any integer value between 1 to 255, indicating the quantizer's step size for the corresponding DCT coefficient. Quantization is used to produce additional compression by encoding DCT coefficients with no more precision than is required to obtain the desired image quality. Quantization is intrinsically lossy because it is a many-to-one mapping. In DCT-based encoders, it is the primary source of lossiness. Mathematics of quantization. Each DCT coefficient is divided by its matching quantizer step size and then rounded to the nearest integer. The quantizer step size is used to normalize the output value. Dequantization. Dequantization is the inverse function, which in this case simply means removing the normalized by a function by multiplying the step size, which returns the output to a representation suitable for the IDCT. DC coding. The DC coefficient is a measure of the average value of the 64 picture samples, and it is treated separately from the 63 coefficients after quantization. Because the DC coefficients of adjacent 8x8 blocks normally have a significant correlation, the quantized DC coefficient is encoded as the difference from the DC term of the previous block in the encoding order described below as illustrated in figure 3. Because DC coefficients often comprise a large portion of the total image energy, this specific treatment is worthwhile. Zigzag sequence. Finally, all quantized coefficients are arranged in the zigzag sequence depicted in figure 3. By placing low frequency coefficients, which are more likely to be non-zero, before high frequency coefficients, this ordering aids entropy coding. Entropy coding. Entropy coding is the final DCT-based encoder processing step which accomplishes extra lossless compression by encoding the quantized DC coefficients more compactly depending on their statistical features. Huffman coding and arithmetic coding are the two entropy coding methods specified in the JPEG proposal. Compression and picture quality. All DCT-based modes of operation typically produce the following degrees of picture quality for color photos with somewhat complex scenarios for the stated compression ranges. These parameters are merely a suggestion. Quality and compression might vary greatly depending on the source image and scenario material.
So in this slide, we will be addressing the question why use DCT and not DFT in case of our image compression standards like JPEG. So the first advantage of DCT is it has high degree of spectral compaction, which means the most of the energy in DCT is concentrated in small amount of coefficients. For example, suppose we are implementing DCT on 8x8 block, that is 64 point DCT, then we will be having 64 coefficients at the output, but most of the energies will be concentrated in fewer of these coefficients, not all of these coefficients. So we will require very less storage to store these coefficients and ignore other coefficients which have less energy. To demonstrate this, we have a Python demo wherein we will be comparing DCT and DFT algorithm. So here you can see I already ran this code in which I'm going to compare DCT and DFT. So I am using libraries like SciPy, NumPy, Matplotlib to showcase my results. So here I have taken an image which is called Lena, and it is a grayscale image. As you can see, this is the original image. So original image looks like this. When we divide this image into 8x8 DCT blocks, and then we take the DCT coefficients, we get this kind of image. Now we have not yet compressed the DCT coefficients, like we have not ignored the low energy coefficients which we do not require. And the next step is to ignore these coefficients and keep the coefficients only which have the higher amount of energies, which contains the information regarding the image. So after thresholding our 8x8 DCT, we get this kind of image. This is the compressed form, and when we apply inverse DCT on this image, we can observe the two images side by side. So this was the original image and this was the image compressed using DCT. We can observe few pixels here, like this area was smooth in the original image, but here it is quite pixelated. So but yet it is like comparable to the original image, and the compression has just resulted into loss of few information, hence JPEG is called a lossy compression technique. Next, when we apply DFT on this image, we can observe that DFT gives a lower quality image as compared to DCT. Here what we have done is we have just kept 6% of the DCT coefficient, while we have kept 8% of the DFT coefficients. But still DFT is not comparable to DCT. If you observe the face here, face is pixelated in DFT, while DCT shows a smooth face. We can clearly observe the difference here, and hence we prefer DCT because it has very high energy compaction. So the next two questions which are based on JPEG XL and how it is different as compared to JPEG. What are the fundamental algorithms which makes the difference between them? We will be discussing these two questions in the further slides when we discuss JPEG XL and how it is different to JPEG. This slide shows JPEG XL codec architecture, and it is a lot different from legacy JPEG architecture. We can observe there are improvements made in every stages of JPEG basic architecture, and here we can also observe that JPEG XL is back compatible with JPEG. So if you have a JPEG XL stream, you can use a specialized JPEG transcoder to convert it to JPEG. So it is like vice versa also. If you have a JPEG, you can convert it to JPEG XL, and reverse is also possible. So due to this, it can be the next generation image compression standard, because we already have JPEG in use and we can use this as well. So we will be looking at each of these blocks in detail in the further slide. Let's continue. So XYB transform is derived from LMS color space. The LMS color space represents the three types of cone in human retina, and like our human eye is sensitive to these three types of cones, which represents long, medium and short wavelengths. Here the X part of the transform is the difference between long and medium, while Y part is the sum of long and medium, and the short wavelengths are represented by B. So these are the receptors of human eye. So like defining the colors in terms of these coordinates helps us to encode the image as per the visual properties of our eyes. In practical terms, this allows for using less data for storing the blue signals without losing much perceived quality. So integral transforms are used in JPEG XL. As we remember, in JPEG we used to use 8x8 grid for DCT, and DCT size was also 8x8. Here the grid size is 8x8, but the DCT size is flexible. Therefore, it is called variable DCT method. And here the variable sizes which can be used are 8x8, 16x16, 32x32, and also it comes in rectangular sizes. For example, 8x16, 32x8, and so on. So this allows further reduction in the entropy of the image for homogeneous areas. Suppose we have a area in the image which is uniform with the same color. So using a higher size DCT would help in storing that particular area in less number of bits. And there are special cases transform to better handle the image compression. For example, small transforms can also be used. For in the previous point we observed, for homogeneous areas we can use higher size transforms. So similarly, for heterogeneous areas where there are a lot of variations, we can use smaller transforms so that this variation can be captured easily using these smaller transforms. There are other transforms called AFB and identity, which are like modified versions of the small transforms. In legacy JPEG, we used to subtract the DC coefficient for the previously encoded block from the DC coefficient of the current block, which was known as differential DC encoding. But this prediction mode was very old and it doesn't take into account the bidimensional nature of images. So for that, JPEG XL uses something called as adaptive predictor. JPEG XL has a set of 8 different prediction modes, and based on the behavior of the nearby pixel, this one of these modes is selected. So suppose you have neighboring pixels wherein one of the prediction mode gave you the minimum error. So on the current pixel, that mode will be selected. So if we remember, in JPEG we had choice of single quantization matrix per channel. So what we used to have is quantization table which we used to quantize the DCT coefficients, and this table was constant for all the DCT blocks. But in JPEG XL, because we have variable DCT used on different blocks, we can have different quantization matrix for each of these blocks, and even further this quantization matrix can be scaled locally so as to decrease the artifacts in more complex areas. So if the area is having a lot of information, this quantization matrix can be customized for such areas, and this would lead to, without this can be done without increasing the number of bits in other part of the images. So if we do this kind of quantization which is adaptive, the losses all over the area due to quantization would be kept uniform, whereas on the other hand, if we use a plain quantization of each pixels of each DCT coefficient, then it would result in variable losses depending upon the image which is given at the input. So this adaptive quantization avoids large variation, and this is the main difference between JPEG and JPEG XL. DC handling. So banding can be caused by DC quantization. So whenever we obtain DCT coefficients, there is a DC coefficient among them, and when we quantize this DC coefficient, we can observe in both of these images, if we have a gradient like this, it will be pixelated at the output. So to avoid this, what JPEG XL does, it uses finer quantization steps for encoding these DC coefficients which are close to 0. So this helps in reducing the banding effect. So AC encoding in JPEG was done in zigzag order, but in Excel we use different transform sizes. So what it does, it generalizes this zigzag order for those cases, like for 16 by 16 DCT size we would have a different zigzag order as compared to other DCT sizes. So and further, these zigzag orders are not necessarily optimal for a given image. So zigzag may not be optimal for one or the other image if the image changes. So what JPEG XL does, it allows to encode in custom order as well, depending upon the input image. So we can observe ringing effects, which are nothing but, if we observe these two images, here we can observe after compression, the background of the image near the branches can be seen as blurred. So this is called ringing effect. So this is caused by quantizing the higher frequency components, like the higher frequency DCT coefficients. And JPEG XL tackles this problem of ringing by using loop filters. So loop filters can be a smoothing convolutional filter which can smooth out the image after compression. So this would reduce the ringing effect, and hence it is better than legacy JPEG. So entropy coding in legacy JPEG format offered us two choices, that is Huffman coding and arithmetic coding. But these entropy coders have their own disadvantages. For example, arithmetic coding has slower decoding speed. So to tackle this, JPEG XL uses a newer scheme which is called asymmetric numerical system, and this is a new recently introduced entropy coder that achieves compression ratio similar to arithmetic coding, but it uses significantly less time during decoding. And the JPEG XL encodes in a single ANS stream symbol drawn from multiple different probability distribution. So, but this would require significant amount of bits. So what it does, it divides the stream from different distribution into cluster with similar distributions, and with a single histogram being encoded for the whole cluster. So this solves the problem of using higher number of bits. That is, clustering is the technique used. So JPEG XL has something called as JPEG recompression mode, wherein you can supply a JPEG file to this standard, and it will compress it further and convert it to an JPEG XL file. So how does it converts an existing JPEG without further loss? So it improves the DC prediction of the JPEG file. Also, it improves the entropy coding and the context modeling. The coefficients are reordered to make it more efficient for compression, and the simple codes for quantization tables and Huffman codes are used instead of more complicated codes which are not required. So prediction, and there is something called prediction of lower frequencies from DC. So these all methods reduces the file size further from JPEG to JPEG XL. So this slide shows comparison between JPEG XL and other JPEG and other standards like HEIC. Here we have minimum mean opinion score which are taken from different individuals. So here we have 26 subjects, of which 11 are female and 15 are male with different age groups and so on. And here they have given their score, which is called mean opinion score, wherein they compare the original image with the compressed one and score it between 1 to 5 score. And here we can observe in all of the curves, the violet curve, which is JPEG XL, outperforms the curve for legacy JPEG, which is the green one. So at even the lower bit rates, for example here for John's screenshot, even at bitrate of 0.5, a person could not have distinguished between the original image and the compressed image. He gave a score of above 4.5. Similarly, in other curves also, for portrait images, sailboat images, JPEG XL outperformed all the other JPEG standard. So this was a result which was obtained from this white paper, and it shows significant improvement in terms of compression rate and the visual quality of the image after compression. And these are the references which we used. Most of them are from the official website of JPEG XL and other.